In this video, we're going to study one of my favorite integrals. It's the Gaussian integral. This is the integral of the function e to the minus x squared and then integrated over all possible real numbers, minus infinity to infinity. But this integral is interesting for multiple reasons, and one of them is that the answer, if I may spoil it, is just square root of pi. When you look at this, there's no sines or cosines, there doesn't appear to be any rotations, sort of periodicity. Why is pi here? So we want to try to solve that. We want to figure out how to actually do this integral. And I'll also note that what this looks like, this is the graph of the Gaussian, e to the minus x squared. This is an extremely common distribution. You find it all over the place in probability and statistics. Indeed, when you look, for example, at the grades that students get in a course, it typically tends to have this kind of normal distribution, hopefully not centered at zero, but nevertheless a distribution that looks a little bit like that. So the Gaussian integral is very important for many different applications, and in this video, we're going to see how we can use multivariable calculus to solve what is ostensibly a single variable integral. And indeed, it might be worth reflecting on the fact that I actually don't have any obvious methods to solve this via single variable calculus techniques. There's no, for example, U substitution that works here. There's no integration by parts that works here. And I invite you to play around and see if you can find something. So let's see how we can use it with multivariable calculus. It's an awesome trick. So let me just focus on the integral just by itself, but I'm going to square it. So it's not just an I equal to this particular integral. It's an I squared is equal to the square of that integral. Okay, bear with me for a moment. I can just rewrite this as just the one integral times the integral again. Both of these integrals are with respect to x. However, the variable name inside of an integral is just sort of a dummy variable. The end of this is just going to be some number if indeed it converges. And the label that you put to the indexing variable x is irrelevant. So why don't I keep the first one called x, but the second one I'm going to call y. So I have the same integral sort of formalistically, but the one is in terms of x and the other is in terms of y. And now that I have this, I can sort of play around with the multivariable interpretation that I get. So for example, I can bring these two integrals together if they converge to just be, well, the product of these integrands. Because the individual integrams are entirely in terms of x or entirely in terms of y, I can actually smash them together. They're just constants with respect to each other, so you can sort of move these constants around as you like. Then I'll just use a little bit of an exponential rule. So if I look at this integrand, this product of two exponentials, I could clean that up and make it just one exponential e to the minus x squared minus y squared. So what I have is now putting this all together is this nice double integral with respect to x and y of the function e to the minus x squared minus y squared. It's now a multivariable calculus problem. And indeed, while this is not the original integral, that's the square of the original integral, if we can get the value here, we can just do the square root and get back to the final result that we need. Okay, so how can we do this? Well, in Cartesian coordinate systems, it's still challenging. I'm actually no better off than I was before. But one of the things that we know from multivariable calculus is that if you change coordinate systems, you can sometimes turn an integral which is hard to solve into one that you actually can do. And this is exactly an example of this. If I plot this function, it kind of looks like this. It's similar to the single variable Gaussian that we saw before and we said was so important in mathematics, but now this is a two variable Gaussian. And I want you to note that it has a sort of spherical symmetry. If you're standing at the origin and you look in any direction, it looks exactly the same. And so this is a perfect example of a function where polar coordinates make sense. And polar coordinates is all about you choose some theta value that tells you the direction in which you look, and then you get an r value, which is how far down in that particular theta direction should you travel. So let's convert it to polar coordinates. And indeed, that is going to look like this integral. If I look at the integrands, I see a minus x squared minus y squared and a minus r squared. And indeed, this is just the definition of the conversion from Cartesian to polar coordinates, that r squared is x squared plus y squared. So that works out perfectly fine. Then if I look at the little area, in Cartesian it's dx dy. And indeed, we've studied previously when we introduced polar coordinates that when you take the little area in Cartesian and convert it to polar, it becomes r dr d theta. Remember that r out the front. It's an important part. You might forget about it easily. You might think it's just dr d theta, but no. The conversion to polar is r dr d theta. Then for the limits of integration, well, in the Cartesian, it's all values of x and all values of y. So in polar, I want it to reflect the entire plane once again. So basically what I'm doing with the 0 to 2 pi is taking all values of theta. I can look in any direction. And then if I choose any of those directions, The r values go from 0 to infinity. I'm saying I'm allowing all possible r values. So both of these double integrals represent the same region, the entire plane. Note that there's no need to include negative values here, because if you take theta and add pi to it, that just sort of rotates your view 180, which is the same thing as multiplying by a negative sign in your r. So our r's are just from 0 to infinity. Okay, well, after that conversion's done, now it just becomes a question of, can I integrate this thing? This is just some interval. And the answer is that now I can. Previously, I had a problem because of the issue that I couldn't do a u substitution. If you tried to make u equal to minus x squared, there was no x to be the du. But now I have such a thing. So I'm going to set my u to be minus r squared, in which case my du is going to be minus 2r dr. And then I know that this is an improper but definite integral, one where I have limits of integration. If r was 0, then what is the u value at 0? Well, minus r squared minus 0 squared, it's just 0. Likewise, if r was infinity, then u, which is negative r squared, is negative infinity. So my new bounds on integration are going to be 0 and minus infinity. And indeed, if I plug it in, the outer integral doesn't change, but the inner integral does. It's got the new bounds on my integral sign. And then my integrand is simplified to be e to the u, but I have to pick up that negative 1/2 because the u is equal to minus 2r dr, and I only had an r dr before. This is just an exponential, so I can integrate that. And then focusing just on that integral, I have to evaluate it, the 0 and the minus infinity. E to the minus infinity is 0. E to the 0 is 1, so I have to subtract off the negative 1/2. And so my integral is from 0 to 2 pi of 0 plus a half, or in other words, just a half. And then that's just a constant, so I multiply by the 2 pi, I get 2 pi times a half, in other words, I get pi. That was just computing now that we've done the hard work and converting. So what I've determined is that my original integral square, remember that's what we've been working with the entire time, is equal to the value of pi. Get rid of the squares by square rooting on both sides, and my original integral, my Gaussian integral, is now equal to root pi. And that's our final answer. So I really love this approach of taking a challenging integral in a single variable calculus and converting it via a little bit of a trick into a double integral, where we could use new tools that were not accessible to us in single variable calculus, like changing the coordinate system to make it a little bit easier. And indeed, in this case, changing to polar coordinates was a very natural thing given the symmetry of the function we were considering.